Good morning, everybody. Welcome to the symposium. Today we'll be listening to talks by Éle Donegan and Andrew. Forgot your last name. And I'm going to be focusing mostly on the drone project. Thank you for coming and listening. I'll pass it on to Éle to continue.
Thank you. As Farah said, my name is Éle. I'm a junior at Yale. I spent the summer in the Newburgh group working on the drone team. My personal project was, yes, 75% of this demographic. My personal project was upgrading the receiver system and amplifiers of the drone and transmitter system. A little bit of a mouthful of a title, but it was like my research proposal title, so I thought it was a good one to use today. And hopefully I'll explain what it all means. Okay, so why is this important? Basically what the Newburgh group is working to do is to get a better understanding of dark matter, especially the role it plays in the expansion rate of the universe. There's a long process to get to that final question, like answering that final question, but it starts in this lab. I'm working on building really precise instrumentation. So there's work on the beam characterization of the telescope, and that requires the drone that I'm just going to talk about later, my signal chain, a lot of fine details like Morgan's antenna. It's all the team effort that comes together. Yeah, the signal chain is a small part in this larger project, measuring the 21 centimeter neutral hydrogen emission, measuring the redshift from that, mapping. Oh, I should go on the next slide actually. This is from Audrey's thesis. It was a really good summary, and I thought I'd steal it for today. Yeah, we worked on the characterization. We want to measure the redshift, and then we're able to trace distant galaxies, and that allows us to map the early stages of dark matter in the early stages of the universe. But yes, it starts with the very precise instrumentation, which is what I'm going to focus on today. So this was my personal project, was to improve the signal chain at the receiver end of the feed, so attached to the telescope feed. Those two main things I wanted to worry about. So I wanted to be able to boost the signal of our target frequency bandwidth, and then filter away all the other signals that we were receiving, because it's a broadband telescope with signal-ish. So we wanted to get to that really narrow frequency, and also to lower the overall noise temperature of the signal chain. The previous one was really noisy, so it's really hard to even see what signal we were trying to look at. So we wanted to limit all of that and then boost the target signal. This is the old signal chain. The little three things in the middle are the amplifiers. So their job is to boost the signal. That's essentially what they do. And then at the end, they're the filters. So this filters out the other frequencies that we're not interested in. So I had sort of three questions I had to answer, which was where should the amplifiers go in what order, because they all have different attributes. And then where should the filters go in the chain, and then where should the cable go that currently connects the feed to the signal chain. And we wanted to play around with the position of that. So I got to do a lot of hands-on practical work, which is really cool. The first thing I did was measure the gain of each amplifier. I hooked it up to the VNA, wired it with the power supply, and looked at the output on the spectrum analyzer. Really cool equipment that I got to use thanks to everyone helping me how to learn to use it. Measured each of the amplifiers. That was a pretty easy task. Found it pretty quickly. They all had their own individual gains, and they were all different. It's kind of trivial which order you put them in when you're just thinking about gain, because the overall signal chain will just be like an accumulation of that. But it's kind of nice to put the biggest gain first. But what really helped me decide the order was the noise temperature test. So these are my two setups here. I'm just going to jump to the next slide to explain why I did those setups. So for the noise temperature, I wanted to take a temperature measurement of how each element would react into extreme temperature conditions. So we had the hot, which was room temperature, so I measured it to be about 295 Kelvin in the lab. And then the cold, which was 77 Kelvin, which was liquid nitrogen. And then we find a ratio of those two. This is the second equation here. After converting it from log to linear, we find a ratio, which is the Y value. And then we can plug that into the noise temperature equation, which is how I calculate the noise temperature of each element. T hot being 295, T cold being 77, and the Y ratio being the most important thing here. So in order to do that calculation, I had to get the data. So I built this setup using things we had in the lab. I clamped each element in, powered it, power supply, and then would lower that little cable thing into the bucket of liquid nitrogen, and each element would have a coaxial cable attached to it, and then a 50 ohm resistor on the end to terminate the chain. And I would take a measurement after dipping it in liquid nitrogen, letting it rest for about 30 seconds so it would actually get to 77 Kelvin, because if I didn't, it would be about 120 because of the bubbling just reacting to the cold temperature. Filter it back out and look all the data that I got. So, and I did this Python script to load the data, read it, convert it, do all those use these equations that I got in the microwave engineering textbook. And this was basically my summary of what I found. So this was the 3 amplifiers. The previous signal chain had this amplifier first, which actually had the lowest gain and the most noise. So I don't really know why that one was first, but I knew to put that one last. And then we had this one last, which is actually the best one, which is the highest gain and the lowest noise temperature. There was some disparity between the sheet and what I measured for the noise temperature. So I think I didn't let it rest long enough before I took my initial measurement, because when I worked backwards, I found that the peak core temperature was probably 120 Kelvin and not 77. So in future iterations of this experiment, I would leave it for longer in liquid nitrogen to let it actually cool. But I did match the findings of the order of what was the most noisy to the least noisy. So there's an arrow, but you can't see it, but that was good. I figured out the noise temperature and the order of the amplifiers. And then the next step was figuring out where the filter should go. So you can see these are 2 plots I did using all of my data that I got. The blue is the old signal chain, and you can see at the end there was a big spike. They didn't successfully filter out the higher frequency signals. So I knew that I needed to add in a low pass filter to fix that. So I added in a 750 low pass filter, which filtered out those higher frequencies. And then I also figured out that having the filter first just made it more exact in the filtering and a cleaner cut. So if you see the orange here is when the amplifier is first in the signal chain, and it just didn't filter those inner target bandwidth frequency as much as we'd like. So that's how I figured out that the filter should go first, and then the first stage amplifier, and then another filter to really get that clean cut, and then the rest of the chain, and then the additional 750 low pass filter that the old signal chain didn't have. Okay, so this is just proving my results that I did in fact lower the noise temperature of the signal chain. I started off just doing calculations using those equations that we found in the textbook, and I had some predictions of what I should be able to see. This is also when I started to consider where the cable should go in the signal chain. So that was part of my calculations that I put in. If I jump back to this slide, I also had an equation for lossy elements and how they get the most temperature of that. So the cable is a lossy element, so those are the equations I used to figure out that. I'm jumping ahead. So then I took more liquid nitrogen tests. I didn't change my setup because I wasn't able to clamp a whole signal chain onto that little piece of wood. So I didn't make a new setup, but I did find that I was lowering the noise temperature significantly. If you see the blue on this graph up here is the old signal chain, and its noise temperature is so much higher than the orange, which is the new signal chain. And that just shows it again here, except I was showing 2 options of having where the cable should be. And it just confirmed to me that I should have the cable actually third in the signal chain. So that added a whole new element to consider. So this is our final 2 options for the signal chain, and having the cable as the third element was a lower noise temperature. So that's what we're going to continue with. So yeah, it's going to go in here. And that brings us to the future steps. Today's my last day in the lab, so I'm not actually able to finish doing this. But now that we want the signal chain to have 2 elements before the long cable, it's actually going to be outside, so we have to weatherproof those. I ordered a box and laid out plans of how we're going to do that, but those are the boxes. And then once the dish, the telescope dish, for those who don't know, has been decommissioned. So when it finds a new home, we'll do some new measurements with that to see if it's working. But I was able to get some measurements in before it moved, and there was better signal sort of filtering and amplifying with the new chain and the old chain. So yeah, I just want to say thank you to everyone who helped me this summer. Morgan, Pranav, Audrey, other Audrey. It was such an enjoyable time, all such wonderful intelligent people. I had a lot of fun getting to be Andrew's helper flying the drone. I'm really excited to see everything come together when they get the new signal dish, and when Morgan flies the drone in Green Bank. I think that's really exciting. Yeah, it was a privilege for you all, and I had a really good time. So I hope that made sense and you enjoyed it, but I want to leave some room for questions if possible.
With the new radio dish, do you expect your results to vary anyway, or is it like applicable type?
Actually, I was thinking about this because Dr. Will was talking about his thesis. In his thesis notes, he talked about the setup here at Wright Lab. And in the old dish and the old signal chain, he wasn't able to get any reading of signal. So I'm hoping that with the new location of the dish, with the new signal chain, we'll actually be able to get some sort of data. And given that it is a better amplification and that it's better filtering, I'm hoping that and less noisy, hopefully you'll be able to see something. But yeah, so we'll wait and see. But